Well, good morning, everyone. Over the past week and over the next couple of weeks, most of the lectures that you've heard and will be hearing are by university professors. And the same is true when you come home to your universities and you interact pretty much with people from academia. But in fact, there is life outside of academia. And I know after talking to many of you this year and previous years that most of you are actually quite interested in what is going on in industry and industrial labs. And so we today invited three distinguished researchers who will tell us about research at various industrial labs. This morning, I would like to introduce Lisa Amini. She is the director of IBM lab in Cambridge, Massachusetts, which also includes a pretty remarkable entity called MIT IBM Watson AI Lab, which I am a proud member of. And Lisa, as you will tell you all about it. Lisa also, a few years ago, was the founding director of IBM Global Lab in Ireland. And in fact, Lisa was the first woman ever to run a global lab at IBM. So let's welcome Dr. Amini to our summer course.
Thank you, Boris. Thanks, everyone. Good morning. This, as Boris said, this is I'm from industry, so it will be much more of an industry flavor. But I've also tried to make sure it's well grounded in the in the research. Just maybe a little bit about additional in my background in terms of my path to AI, because I actually my PhD wasn't in AI; it's in computer science. But I started out more in distributed systems, and it was around 2000, early 2000 is when I started doing machine learning, primarily in terms of stream data mining. And then from there, we started to realize okay, it's great in terms of being able to find signal, in the data. We could do that relatively easily with the right number of PhDs applied to the data. But the problem was we weren't kind of building up momentum in terms of persistent knowledge base. So I kind of took a turn for a while and really tried to work on and understand knowledge representation, knowledge acquisition from data, trying to bring that into knowledge bases that could be used for AI. And then in 2017, there's a decision to build this new MIT IBM Watson AI lab. So I moved from the Yorktown lab, which is our main headquarters for research, to the Cambridge lab to help work on that. So and as Boris said, it's just really a fantastic thing for us. We're really excited about it. And so what I'll be doing today is I'm going to take on the area of automation in AI, or auto AI, if you haven't heard of it. This is an extremely important area in my mind, not only for industry, but also for academia to understand and to contribute to. So I wanted to cover that, and throughout what you'll see is I'll be citing papers. The blue names mean that it's an IBM, the red names are MIT, and the white names are papers that I thought it was important to reference to try to give you the whole picture. So that's the guided tour, and we'll get started now. Okay, just if you'll indulge me, just really quickly, not everyone has worked with AI research, with IBM Research, so I just have two slides to try to explain what we do in IBM Research. So there are roughly 13 labs worldwide, around 3,000 researchers. The different labs, in some cases specialize. For example, the quantum computing research primarily happens in Yorktown, a little bit in Cambridge, and Zurich and Almaden, but mostly in those areas, not so much in some of the other labs. Whereas AI, cloud computing, that tends to happen kind of pervasively across nearly all of the labs. We also take very much, we go after, while we are in industry, and we're looking to apply this. We also are very much going after more of the same types of publication venues and accolades that researchers in academia would. So as you can see here, IBM researchers have been, Turing Awards, National Academy of Sciences, Engineering, and so on. So not everyone at IBM Research is a Turing Award winner. I am not. But it's great to work in an environment where, the goal is to do really high quality research that tries to not only impact technology, but also tries to advance the science. So that's just a little bit about IBM Research, and now I'll move into the topic that I really want to cover for today. Okay, so starting a little bit broad in terms of the evolution of AI. So what I want to do is I want to start putting a bit of an industry face on AI, right? So probably what you're hearing a lot in this course, because it's focused on understanding that combination between the brain and what can we learn from it, and cognition, and how can we bring that to AI. What I would say is that this goal of general AI, as a researcher, I believe it's actually fairly common that we feel like that goal of general AI is probably at least decades away, right? It's a very tall order to actually be able to achieve that. And what we have today, frankly, is actually very effective in various industry areas, right? So we can take a set of data, images, for example. What's shown here is images in terms of dermatology images. Take that training set with labels, be able to train a model that can actually, identify, cancerous, non-cancerous, regions better on average than human experts can do. So very focused tasks, very well trained models, on data, can do very well, and that's a huge impact for industry. But there are many, many shortcomings of that, right? So what I just described in terms of being able to take those images, if you were just to, for example, in many cases, just change maybe the camera, for example, going from optical imaging to something that maybe sits on the skin and goes slightly below the skin. You start over, right, in terms of trying to train the model, collect the data, label it, train the model. So you start over. So the models we train today, they work on a single task, in many cases kind of for a targeted, with limitations on the data set. It's not everything, right? Obviously, images, many of the images you see, like ImageNet, weren't all taken with the same camera. But I'm just trying to emphasize the point that it's not just like you train a model and then it works everywhere. So this area kind of in between is where we feel like the important research today, a lot of this is happening. And so what we try to do, especially with the MIT IBM lab, is to try to look as far as out in terms of the general AI or the complete AI that we would like to achieve, and then try to tackle tasks that help us to get there. And along the way, try to sort of broaden what AI can do, make it more robust, make it more applicable to different tasks, make it so that it's explainable, more trustworthy, and all of these sorts of things. So that's the area that you'll see a lot of the work that I'll talk about today is kind of in that space of broadening AI. Okay, so now switch and talk about AI in industry, right? So there's a lot of work, and frankly, it is correct that even in industry, we do have a need for image analysis, but a lot of what you may see in terms of publication are image analysis of more common things, everyday things, cats and dogs and buildings and these sorts of things. And that's important, and frankly, the reason why it's so important is for many, many years, that was the hardest task, right? So we had ways of kind of making progress on some of the natural language things, on being able to form predictive models from structured data. But really doing good vision for many, many years was a challenge that we just couldn't break that barrier of doing better than humans could at even just visual object recognition. So big breakthroughs there with deep learning. And in many cases, especially for companies that are focused on interfacing with consumers and broad sets of people, then these types of common images can be very important. But there's another side of industry that it's important to see, right? So this is a picture of a processing plant. Anyone want to guess at roughly how many sensors might be in a processing plant like this? rough order of magnitude? Hmm? Yeah, pretty close, right? Hundreds of thousands. We find 600,000, 700,000. So yeah, it's huge, right? And you can imagine, right? I mean, many different sensors, many different devices, many different combinations and contexts for those sensors. And so, how do you go after that? Frankly, this type of structured data, for the most part, is still using some of the more traditional machine learning methods or ensembles of those machine learning methods, as opposed to deep learning, just because the ability to kind of get that labeled data to do supervised learning, for example, isn't there that you would need to do deep learning. And it's not just it's not just the sensor data that poses problems in terms of what we have today for AI. Another example is just in terms of the images. Well, sorry, I just wanted to point out, right? So the point is that some of these are kind of give you a nice warm fuzzy feeling, you go after them, but this space over here is definitively not warm and fuzzy, and it's very difficult, very challenging to go after. So even in terms of object recognition, so simple object recognition, it's not like you're recognizing well-known things. Our customers would like to recognize pieces and parts that they may find in motors or airline or a processing plant or these sorts of things, and they're not always in a nice context. So this is new challenges as well. And even if you think of the text, so if you look at news articles and trying to extract facts from news articles are actually written so that the facts are there and easy to attain, right? It says who did what to whom when, right? And you can start to pull those out. And so this automated knowledge-based construction leverages that facts, that ability to try to pull facts much more easily. But if you look at this type of text, this was extracted from a regulation that banks need to understand. And it's not like the others where it's factual, right? Who did whom to what. Instead, it's trying to say, this is a desired state that the world should be in, right? And then humans have to try to read this and then try to map their own entities, banks, customers, loan agents, onto the different entities that are within this. So it takes a lot of human inference even to understand that this is well beyond the inference that's required to try to extract facts from news articles, for example. And I'm not saying that extracting facts from news articles and bringing that into a representation on which you can easily reason is that easy. I'm just trying to describe that there's things well beyond that to try to achieve. Okay. And now if you look at behind the scenes of how this often happens is, if you look at a lot of the academic papers, if you're only looking at the academic papers, then what you'll find is they may be doing evaluations on standard data sets, right? So ImageNet, NIST, and so on. And that's important because that enables us to benchmark algorithms against one another in a known space. But the problem is that then how do you take those algorithms, those advancements, and then try to apply them on your data? Well, actually, you have to start by even collecting the data and labeling the data and deciding how you combine different sets of data together. So it's a very messy and ugly pipeline that is often happening behind the scenes when you see these breakthroughs and people try to bring them to industry. And in fact, that's just the beginning of it. That's the data science pipeline. And then once they've gone through and someone has a model and they feel it will work with their data, okay, then you have to deploy it. And when you deploy it, things happen, right? It has to stay up and it has to stay available. The data may move on. In other words, you may be analyzing and doing predictions or classification in a certain area. New devices come along, new people come on board, and then suddenly your models are no longer relevant. So how do you learn from what's happening in the field and try to bring that back into the training process itself? So literally right now, a lot of this in most places is being done by, each of these steps is a human that's going out and trying to perform these steps. And auto AI is basically saying, okay, well, which parts of this can I start to automate? How can I use AI to try to make this so difficult and cumbersome and frankly error prone, right? So I can tell you what's kind of happening today in industry is that people are doing their best, right? They're trained in data science. They have these different things that they read in the papers. They start to try to apply it. works or doesn't, and then they just keep trying to churn and overfit and make it work. And then when it makes it work, then they make it work and they're getting good accuracy, then they deploy it. But then what happens, as I said, is the data that they're seeing in the field doesn't look like what they actually trained on, and then they're struggling with this. So it's a very challenging space. So the idea is, could we try to, with automation, make that better? Could we try to bring some best practices so the machine is, in an unbiased way, trying to perform some of these steps so that you can move away from some of this overfitting and bias and so on. So that's the idea behind why we feel auto AI is so important. So what is auto AI? Okay. All right. So for us, we think of automation of AI as being able to design the actual neural networks themselves. And in fact, what I would say here is that because of the use cases that I was showing earlier in terms of processing plans and so on, it's not just these deep neural nets that need to be designed, but also using traditional machine learning algorithms on structured data is an important area for designing the networks or the architectures as well. So we want to try to use AI to design the networks. We want to try to use AI to then optimize over time, both what's happening in the data science area, but also as it's being deployed and trying to bring that back. And then AI, hopefully also to manage it, right? To look at whether or not, for example, if there's bias that's showing up in the data, could we help with trying to explain the results that are being seen and so on. So we try to look across this whole spectrum and build these auto AI methods for both deep learning as well as other traditional forms of ML. Let me stop for a second and just see if anybody has any questions. So is this stuff you guys already all knew? No, it's okay, a little bit. How many are familiar with auto AI already? Okay, got a couple. Okay, doing auto AI research? Yeah, okay, cool. Keep me honest. Okay, all right, so what I thought I'd do is to just try to go a little bit under the surface of what is auto AI. And this is kind of the fundamentals, the basics of it, right? And then we'll get more deep in a moment. But the basic way that auto AI works is that there's kind of three main components, right? So the first thing is you have to decide what are you going to be searching over? Because literally it is neural architecture search, right? That's what you're doing. You're trying to search for a configuration of a neural net and the parameters that go with it that is going to achieve high performance on a particular set of data, or sets of a particular type of data. So first is you have to decide, okay, what's the search space, right? Am I going to be using 10H or LU, the convolutional neural nets, these sorts of things? Secondly, there's the search strategy, right? How am I going to try to look across all possible combinations of these different operators to try to find an effective network for this data? And then very closely coupled with that is the evaluation strategy, right? So you have, what you're trying to do is you couldn't possibly search the entire space. You couldn't possibly test and evaluate the entire space. So you try to effectively decide on which are those architectures you want to evaluate, and then you have your evaluation strategy against this. And so this is kind of the basic components of how people go about neural architecture search. Okay, so the early versions of this started off with just linear chains of neural networks. And while that's certainly not how people design neural networks today, it was important to kind of start somewhere. And very quickly, they started moving to this kind of multi-branching. And this too looks a little bit old and dated in terms of the neural architectures today. But nonetheless, if you think about, for example, ResNet and DenseNets and so on, they were versions of these kind of multi-branch types of neural networks. But more recently, what people are doing is more of these kinds of blocks. What they're saying is, even the humans are looking at this and saying, well, I can't possibly figure out all the combinations that I would want to try to use for my architecture. So instead, maybe what I can do is I can find these cells, kind of these blocks of networks that do well, and then maybe I can put them together in different ways. So that's advantageous for the humans to do, and it's also an advantage for the machines to do, to try to train the cells and then think about how you, or try to identify the cells that are appropriate and then try to also identify how to put those together. In terms of the search strategy, people have been doing a lot of different types. You might think of random search as something, okay, that's the one that doesn't really work, and in many cases, that may be true. But in this case, it turns out that random search strategy with a well-crafted evaluation structure and kind of set of operations actually can work surprisingly well. However, most of the work today, I would say, is more in the area of either reinforcement learning or gradient-based approaches to that. And so what I'll do is I'll give you a couple examples of those and then use that to continue to build up the information here. Okay. And then just one more word on the performance evaluation strategy, right? So the idea is, as I've tried to make the point, obviously you can't search and evaluate the entire space. And so you have to find ways to evaluate it, not on the entire data and not on all the possible things. So generally what people are doing is they will maybe identify a subset of the data so they can sample the data. Or if it's image, they can go against low resolution versions of the images. They can reduce the parameterization or maybe do some filtering or these sorts of things. So they can both try to reduce it in terms of the actual information, the data that is pushed through the network, but also in terms of saying, okay, well, it looks like this is how it's learning, and if I extrapolate out from that, this may be my best path to follow, and then try to do more search along that path. So that's an important part of the strategy as well. And then finally, this weight sharing and one-shot learning. I would say this is kind of the core of where most of the work is happening today. So I'll give you two examples of what I mean by weight sharing and one-shot. Okay, so first one, and this is what I did is I started with two papers that are, I don't know that they're seminal at this point, but I think they're certainly kind of, if you trace a lot of things back, this is where a lot of it came through in terms of kind of the modern methods for auto AI, right? So the central idea here is, this is not a neural network, the network that's drawn here, right? So I want to be very clear about that. Instead, this graph it's a subset. It's meant to sort of represent what could be the entire search space that we could go against, right? And then the point is that each one of the nodes is a set of parameters, operations, and then the model, the information flow is going through the edges. And the advantage that they're seeking with this is that as you're going along this network, this directed acyclic graph, the child nodes inherit the parameters from the parent nodes, and so that reduces the amount of computation that has to be done. So it's kind of the general central idea for this approach. Okay, so as an example, one of the things that it designs is these recurrent cells, and it uses an RNN controller in order to do that. So basically think of it as taking this graph on the far end and sampling, which of those nodes it's going to use, and then how it's going to apply parameters within that node, right? So it samples this space, and so what you can see is the search space is, 10H, rectified linear units, and so on. So it's just making those decisions of which operations and how the information is going to flow through here. And likewise, what it's going to do, it's going to use convolutional neural networks, both kind of for smaller cells, as well as to try to kind of put together those recurrent nets or different cells into a larger structure. And what it's doing here is it's just basically making a decision in terms of these different operations, 3x5 in terms of the convolution, 3x3s, 5x5s in terms of the convolution, so the number of operations, and then a reduction step, and then the number of convolutions, and then the reduction step. And it limits in terms of the kind of how much it's going to do across that. Basically, it goes through the path, or it does like a stride to across that. Okay. So then once it's done this sampling, what it's doing is trying to train, and it basically uses this alternating technique to try to train the sampled architecture kind of all the way through. And then what it's going to do is it's going to come back and it's going to train the controller, this LSTM, trying to use either accuracy or perplexity as the reward to try to find that. And then once it's done that, and it finds some sampled architectures that look good, then it's going to come back and it's going to try to do full training of the parameterization across that. Okay, so this is just one example. I'm going to show you two examples, and then I'm going to show you how it works. Okay, an alternative approach, and again, this is not a neural network, and in fact, it's not the same DAG that we were just looking at in terms of the parameter sharing version. Instead, what's happening is that it starts with the operations are along the edges, okay? And starts with not knowing the operations that it's going to assign along the edges. And then what it's going to do is it's going to iteratively assign operations, and then the training, the whole point of this approach is that instead of just using the reinforcement learning approach, it's putting it into a space where it can use attention and gradient-based methods to try to decide on the weights that it's going to put on those operations. So those colors are different operations, and what are the weights that it's actually going to put on those as it's going across the network. So it searches for the network in this way. Okay, so I know I've kind of gone through this a little bit quickly, but I guess what I want to do is try to lay out the space and then give you an understanding of, so how does it work in practice, right? What do we see? Maybe it could help to ground this a little bit. So these are probably state of the art. So you can see NAS, one of the original NAS architectures. You can see ENAS, which was the first parameter sharing methodology that I showed you. You can see DARTS, which is the second one that we saw, which was the gradient-based approach. And you can see random. So one of the first things that's a little bit surprising, actually, is that the random version up above, this random search baseline at 59.4 is surprisingly doing very well, right? If you compare it to, for example, so I should have mentioned, right? So perplexity, what you want is a low score. This is basically how well the distribution that it's information theory measure, how well does the distribution that you develop actually predict a sample that you're going to get from this. So what you can see here is the random is doing surprisingly well against ENAS. But the DARTS is actually doing best in terms of kind of getting that perplexity. So accuracy, you can think perplexity in terms of a measure of accuracy. So DARTS is doing very well against accuracy. But speed-wise, ENAS is doing better. But look at the numbers, right? Search costs, right? So NAS, 1,000 CPU days, right? This is huge, right? Or 10,000 CPU days, right? So, and this is bringing it down, but we're still on the order of CPU days justifying the architecture. This is not necessarily even being able to, run these architectures, which in many cases, because they are automated found, in many cases they aren't that, they can be computationally complex as well, compute intensive as well. So to give you an example, right? So one of the more recent work, so now we're kind of, what I've talked about so far is kind of the baseline. So now we kind of move on a little bit and take a look at, okay, what are people doing now to try to build on to this? So one is, okay, well, what the original work was doing was to try to just design these networks, and it wasn't necessarily looking at the underlying hardware. If I understand what the hardware is that I have available to me and I have some characterization of that, could I do better? Because obviously this is not great, right? So this probably this first came out with NASNet, right? Being advertised as taking 48,000 GPU hours just to train for ImageNet, right? The previous hours that you were seeing were for the Pentree Bank, and that is that's text, and so it's a much lighter workload. But when you start to move to images, then we've got a real problem in terms of the amount of CPU that it's taken. So there's actually some recent work that what it's doing is it's taking those same types of architecture search approaches, but what it's doing is it's bringing in information about the actual hardware that it would be deployed to. And with this, they were able to show that essentially they could bring down the amount of CPU, GPU time that it's taken for these networks on the order of 200, right? So a reduction for 200x, which is huge, right? So this is an important area. Is okay, how do we go from just being able to search? How can we make it more efficient? Another important area that we're working on is basically saying, okay, well, remember those long pipelines that I was showing earlier, right? How do we go back and tackle not just that one square of the parameter search? How can we kind of bring into consideration the data along with transformations of the data along with the architecture that I'm finding, right? So it's not just adding, specifics in terms of the hardware, but it's also adding how would you manipulate the data to try to bring it into this form. And that's important because obviously finding the right features, the calculations that are required for the features is also very computationally complex and adding to this and makes a big difference in terms of the accuracy that one could achieve. So this particular work is basically using an optimization framework to be able to do kind of a joint optimization that separates it into smaller, easier problems and then tries to build these entire, well, not the entire, so that's why the ... on either side, but trying to build these larger pipelines that take into consideration the data as well. Okay, so I showed you up front some really hard industry challenges. So how's it doing against that sort of data? Because so far, all of the numbers have been against, ImageNet and the Penn Tree Bank and so on. So how does it do on industry data? And how do we figure that out? How do we do this in a way, because we can't just go and it's important that we are also doing something that is in open data that other people can trial against. So the kind of the gold standard in terms of some of these industry challenges is Kaggle. So Kaggle is basically it's an organization. It's been acquired, but originally it started out as an organization where industry and others could post a machine learning data science challenge with data and the tasks, and then people, different groups, can basically go against that task, and there's a leaderboard so you can see how you're doing, and then in the end a winner is chosen, and a lot of times there's kind of cash rewards for it and so on. Kaggle is primarily pursued by humans, teams of humans going after these problems. But about a year ago, we started trying to bring our auto AI techniques with us to try to enter these competitions. We aren't the only ones. Google is doing this, Microsoft is doing it as well. But the whole idea is, can we compete somehow with the humans in terms of trying to design an architecture that would take on these very challenging industry problems? And okay, well, a year ago, 57%, top 57% is where we landed against some of these this particular challenge. But we've been continuing to go after this, and you can see the numbers are starting to get better. I have to maybe qualify this last one a little bit, because it's not that some of this is because we're enhancing our algorithms, we're getting better at it, these sorts of things. But frankly, some of it also is because, and I think I would credit this last one, is that if we can start to reuse what we've learned as we've built it up over time, that's helping a lot. And then what's also starting to help, and in this particular case, is avoiding overfitting, right? So this particular challenge for this earthquake prediction, as you can imagine, didn't have a lot of examples to go off of, right? I mean, how many examples of earthquakes do we actually have, right? So there weren't enough earthquakes kind of in the data to be able to do well with this, with many other types of techniques. And so what a lot of people that were competing in this started doing is they were kind of using the leaderboard to understand what was working, and they ended up with things that were very much overfit. And then when the evaluation data sets were run against it, then it wasn't performing as well. So I would definitely credit kind of both of these. But the point is to say, okay, yes, not at the level of these Kaggle grandmasters, but certainly humans plus using some of these tools, because frankly, it's not that we just entered our auto AI tool and just let it run. Obviously, humans were having to do parts at the beginning and having to do parts at the ends and help to run the auto AI tools. But the point is that humans with these auto AI tools are definitively doing better than without, is the idea. Okay. Okay. I'm gonna. What I want to do is I want to take a little bit of shift to some of the other areas that are not as focused on accuracy, and so I want to just take a minute and see if anybody has any questions. You've been a very, quiet audience, and so any questions or comments? It's okay. I'll keep going. Okay. So what does it take, right? Oh, there we go.
I'm trying to understand, trying to parse kind of at a high level some of the challenges that you guys face that are different than us in research.
Yeah.
Would it be fair to summarize that one of the major differences is that in addition to getting a really good F-score accuracy, you guys are really interested in models that balance the trade-off between accuracy and GPU and resource use?
I would say that's one. So definitely that is one. So we have to care about, how is it going to work in operation, right? Is it going to consume all of the resource that we have? Am I going to be able to, is it going to be reliable and predictable in terms of how, are people going to have to wait too long for the results? So you're absolutely right about that. So that's one part of it. But the other point that I was trying to make is that, and it really depends, right? So if you, the other point that I was trying to make is that going in these types into different domains, it's not like you can just take those algorithms that may have been absolutely the best paper and really move the field forward and just say, great, I'm going to type that in, right? I'm going to run it on my data, right? The data is noisy, it's messy, it's difficult. It's actually, in many cases, it's different problems, right? So, for example, the text that I showed, there's very little research going after that type of understanding of that type of text. It's very important, for people who are in the legal domain, the banking, finance, all of these areas. That's what they care about. They care about, compliance and these sorts of things. And even most companies have regulations. They have contracts that they have to adhere to. And you can imagine if you were able to kind of pull out all those information in contracts so that you knew exactly what you had to manage to, that would be a big win. But it's very difficult, right? And I think the other point that I was trying to make is that what oftentimes people don't realize is that they see these great results, on text, for example, but if they don't understand what it takes to label that content, right, then it's much bigger than what people say. So, frankly, if you look at some of these industry documentation for this, the numbers are that roughly 80% of the time is spent just trying to get the data into a shape where they can train a model. And then, you spend the time to actually, find the right architecture and train the model and so on. But there's a lot to try to get that into that space. And it's not just because the data is noisy and messy and so on. It's because the problems aren't exact in terms of, the translation of the problems. And one could say, not a problem. Once we have general AI, then certainly it's going to solve all of those things. But if you think about it, right, general AI isn't necessarily what's going to solve some of these hard problems. It's not just general intelligence that solves some of these problems, right? Our deal would be to try to go after, intelligence that is, in some ways, specialized, not just general, specialized to try to do, superhuman performance at certain tasks. So, thanks. Hi.
I was just curious, when you started to conceive of different architectures and describe the space, I can imagine that you've already quite some knowledge about what has worked in the past. Based on that, did you observe something surprising with regard to, like, there's always a certain, I don't want to call it superstition, but people tend to inherit lots of features from other architectures that have proven to be successful. Did you find, like, surprisingly successful combination that used your later searches?
Right. Yeah. No. So that's a very good point. So there's several examples of things like that. So one that's kind of getting a lot of press very recently is that for the most part these neural architecture search and even people using them themselves kind of they started to stick with kind of 3x3s and 5x5 in terms of the structure. And the paper from Song Han that I was showing earlier basically found that the architecture was using 7x7, which basically had been discarded by other people as saying, okay, it's not helping us. We can do it well enough with 3x3 and 5x5, right? So definitively by kind of searching that space based off of the data, right? Then in an unbiased way. Then you can get things that are surprising, or at least things that were abandoned, right? And we know this for a fact because neural nets at one time were abandoned as well, right? And currently, a lot of the knowledge representation things are, in some ways a little bit abandoned, right? And I expect that we'll figure out how to do some of those things, but do them with much more differentiable, techniques and so on. So, yeah, we see that a lot, and I think if I wanted to say, kind of that's the in some ways, that's the really important part of auto AI. It's not just make it easier for the humans and so on, but it is, make it better because it's not bringing in our inherent biases against techniques and these sorts of things. Thanks. Yeah?
Our challenges bring the research community to be interested in the industry. I can imagine the warm, hot kitty nature is more interesting than the pipeline.
Yeah. I mean, so here's the thing, right? It's very reasonable that people would prefer to go after, researchers would prefer to go after, things on standard data sets, ImageNet and these sorts of things, just because then they can compare and they can publish, and it makes perfect sense, right? What happens is that we see a lot more of the things that are kind of a little bit more industry. What would happen is it might happen in the the mechanical engineering department, or it might happen in the business or finance or these sorts of majors. Then they start to bring it into research in these areas. What we're doing is more of the computer science version of it, to say, okay, yeah, we know there's all these domains out here, but we can't possibly go and try to figure out every one of those domains. So how do we work on areas that are, can work for those different specialized areas, but are general? And what I would say is that the auto AI community actually is active in research, in academic research as well, right? So, there's quite a few, even at MIT. So Song Han and Tim Kraska, and there's several there. So I think the auto AI. Definitely, we've got research participating in that, both in academia and industry. It's not as big and maybe not as publicized as some of the other areas. So yeah, it's a good point. How could we do better at it is a good question, right? I'm not sure exactly how do we get more people in on these. I'm hoping that some of these tools help to kind of bring people that would be in the specialty areas kind of more in, and so that we can try to advance it together, I guess is the hope. Okay, so I'll try to go a little bit further. So you were talking about bias that may happen in terms of the models themselves or the techniques. Another big problem that we have is bias in the data itself is one example. So the problem is, okay, we want to make sure that when we're building these architectures, when we're training on the data, that we're not just looking purely at accuracy, right? So you've probably seen some of the reports in terms of, well, hey, guys, the image recognition or facial recognition, gender recognition is doing much better with light-skinned males than it's doing with dark-skinned females. So we've all seen those reports. But I can say that problem is pervasive, right? So think about it. If you're trying to come up with something that is going to try to predict, or classify whether you should, accept or decline a loan or an insurance claim or any of these sorts of things, right? Humans made those decisions in the past, right? And those humans could have been biased in making those decisions. And so that's the labeling that the machine is training off of. And so it's very easy for us to fall into this trap or this challenge of models that may be biased. And so the point is that we're trying to. We have part of our initiative is this Trusted AI initiative, and the hope is that with that Trusted AI initiative, that not only they're able to come up with some of these algorithms, and I'll talk about those, but my whole point is that we could then use the auto AI techniques to try to bring in and apply this. That to me is so important because some people have commented, I say I'm trying to work on this auto AI work, and they're like, oh great, more people who have less knowledge trying to build models and deploy them. Is that really a good thing, right? Why are you doing that? Because they're not even going to have the information that they need to properly evaluate it. They're not experts in this, right? So the whole point is, okay, but right, if we can use the tools to try to inject in these algorithms and techniques that can evaluate for bias, that can explain the results in the way that if it's a subject matter expert, that they can understand and do something about it, or if it's a developer, they can understand and do something about it, or a deployment, an operational person, they can understand and do something about it. So a big part of the strategy is to try to build algorithms that can help us with that bias and trust. And one of the first one here is kind of along the lines that I was talking about earlier, right? So this is actually a toolkit. It's out there. It's open source. It's on the web. You can go just Google AIF 360. And the idea is, so you can kind of see the example here, right? So this was someone trying to train a model in terms of trying to do claim approval. And the point would be to give the person who is training the model this information and says, okay, good job, if that's what you wanted, right? If you want roughly 90% of your claims to be denied and roughly 10%, okay, we're kind of hitting about that. But maybe did you understand, or did you realize that, for example, maybe you're denying more for a certain age category? Maybe that's appropriate, right? Maybe that's an appropriate thing. It's just that it should be that those that are in the category of 18 and under, I think it is, yeah, then more are going to get denied. But maybe it's not, right? And sometimes it's obviously much more challenging than that. It may be demographic or just spurious things in the data that are causing these claims to get denied. So this is an important part, and the reason for working on it is so that we can kind of bring it into those auto AI pipelines. Another area is that I think is important, and this, I don't know, Josh Tenenbaum, this is work that's in collaboration with Josh Tenenbaum, and he may have talked about this yesterday. A next area that we feel is really important is program induction, right? So if you look at some of these images here, right? How many blocks are there on the right of the three block tower, right? Will the block tower fall if the top block is removed? What's the shape of the object closest to the large cylinder? So how many of you can answer these questions? Right? Everyone can answer these questions in the audience, but most of the machine learning algorithms cannot. So our visual recognition algorithms don't answer these questions. So a lot of people don't realize that. And the reason is because it's not just recognizing objects, but there's a need for understanding spatial relationships. There's a need for being able to count, right? There's a need for being able to compare. And these are, you can think of them as steps in a program, right, that need to be performed. So the work here that I was referencing is basically trying to tackle this problem to how do we use AI to generate programs. And you can see why, if we're able to make progress in this, even though this is a very specialized space in terms of visual query answering, these types of techniques kind of brought into an auto AI scenario are extremely powerful. So let me explain just a little bit how it works. Like I said, I just wanted to try to put it into a context, right? So, okay, so this is the first thing that happens is basically looking at the scene and then being able to identify, all of the objects within the scene, right? So that's a well-known technology. Train a CNN to be able to do this, and it can recognize, the shiny objects, the different shapes, and so on. And then the point is, okay, we have questions that we want to be able to answer, right? So one of the things that you'll notice is that certainly what's great about this work is it's kind of going into a totally new space and making breakthroughs. But what you'll see is they definitely had to kind of craft their own network to go after this. So the next step was, okay, we have these questions. How are we going to relate these questions to these objects and then perform a program on it? So basically what they were doing was they have a vocabulary of instructions that could be executed. And what they're trying to learn is a relationship between the questions and a sequence of steps, right? And that may seem a little bit odd, but it falls back actually, the original Watson Jeopardy, kind of the big breakthrough I think that a lot of people don't realize there. It wasn't necessarily the whole, that the computer could stand up and answer these questions, but just being able to figure out the question and the intent of the question and trying to match it to an area that could answer it was a big and difficult challenge, in that 2010 period. So this is kind of, in some ways, a much richer version of that matching intention to what are the sequence of steps that we would want to go after. Before it was just matching to potential answers, but now it's a sequence. And then the point would be saying, all right, can we attach these objects to these instructions? So when it says cube, which of the cubes is it referring to? And then basically training across the program execution across the entire thing. Oh, and I missed a slide. But what I was going to say is the reason this is important is because this was basically a brand new challenge, this clever challenge that was put out. And this team came in and basically they just squashed it, right? There was nothing kind of out there, and they came back with like, I think it was like 99.7 accuracy with this approach. So that's incredible in terms of the, just being able to go in and squash it. But, I also want to be clear that, okay, it was very much designed exactly to do this, and it's not like they've solved the problem of program induction. It gives us a really good idea that we could possibly use these, differentiable techniques to do something that prior was really very much in the symbolic world in terms of, planning and these sorts of things. Okay, so this is the material that I wanted to go through. I provided as well some different links that you may want to go in and look at. So if you're interested in the space,